everybody? Rex Bear Elite Project. How the heck are you? Would you just look at it? Oh, yeah. Gareth from See the Pattern is with us today. Really excited about this opportunity. He's one of the few brilliant people that I can understand because I'm just not that bright. And so we're really going to get into the formation today of planets and just why the universe is as bizarre as it is. I'm going to be eating non-genetically modified popcorn and listening to this information, taking notes. Gareth is on YouTube. He's also on Patreon, Twitter, Facebook, and the majority of his work is on Patreon as well as YouTube. Check it out. See the Pattern. He's a regular on Leak Project. He usually shows up about once a month, and he's a very busy person, so I'm really excited to get the opportunity to speak with him. And before we get into this, I wanted to thank my friends over at solarwaterheater.com. Have you got one of these yet? This is so dang cool. I was using one the other day when I went on my Jeep Rubicon trip up there close to the Alpine Loop. We had to turn around because it was too snowy, but we did manage to get some sunlight, and this will actually boil water in as little as 30 minutes. It is fantastic. If you don't have electricity, if you don't have batteries, you don't need batteries or electricity, you just need the sun. If you use the code LEAK15, you'll get an extra 15% off. That's solarwaterheater.com. It just needs the sun. All right, Gareth, man, let's rock and roll. How have you been?
I've been really well. Very busy, as you point out, but that's good. You know, busy at these times is exactly what you want.
Absolutely.
Projects going on, and we're just trying to find out the truth, really. And that's sort of what today's about. Unfortunately, I can't tell you at the end of it that you're going to be any the wiser. I think you'll understand some of the problems and some of the questions and some of the alternatives, but we're going to take you through it step by step. And there are some very interesting problems, I guess, that face us when we look at how planets are formed, which might seem like an obvious thing, but really it's not that obvious. So let's crack on.
I wanted to jump in real quick before we get started because I even wrote this down the other day. I've thought this before, but it really hit me hard. And I knew that we were going to be having a conversation. And it was just a quick note that I wrote, and it said, the moon is not from this earth. The moon is not from this earth. Some completely separate.
Yeah, we will actually talk about them. And I actually did an episode, I think it was only just the other week, about the moon formation and new evidence that sort of discredits the current theory, which is, you know, a completely ridiculous theory anyway, about the origin of the moon. We'll get onto that. There is lots of strange things when you look at our solar system that don't really make an awful lot of sense. Right, let's crack on then. So let's bring up the slides. Buckle up. Right, can we all see that? Yeah? Okay, so in order to talk about planets, we have to talk about stars first. So we're going to cover basically three things. We're going to look at different star formation theories. We're going to then from that expand and look at how planets themselves are formed. And then in particular, we're going to focus on our solar system and understand how our solar system sort of breaks the mold of what we would expect. But let's start by just looking at star formation. Now, why start with stars? I mean, obviously, when you look at the night sky, stars are the things that you see all the time. The sky is littered with stars. And all the models that we will look at basically have stars forming first and planets forming second. So understanding how the stars form helps you to understand how planets form as well. And also, when we look at stars, there is evidence that we think shows how planets form, but I'm going to show you that maybe those fingerprints that we see may not be planet formation at all, but we'll get onto that in a little bit. So let's start by looking at stars. Now, obviously, when we talk about star formation, we are really talking about, you know, if we look out in the universe, there are huge gas clouds, and the idea is that these gas clouds are just sort of floating about. And obviously gravity acts on these gas clouds, and at some point, imagine that they are sort of little particles that float inside of this gas cloud, and occasionally some of them will sort of bump into each other, and they might join together and form a larger clump. And then slowly over time, that clump starts to grow, and as it grows larger and larger, it will attract more and more material. And eventually, as you see in the sort of the diagram, you'll end up with a sort of a cloud being compressed slowly downwards, and that's what forms the star. That's sort of the main accepted hypothesis. So large dust clouds slowly collapse, due to gravity. Gravity is the force that they use to sort of explain that collapse. As sort of it grows, it gets larger and larger, and as it gets larger and larger, the forces get larger as well. I mean, obviously, if we look at the moon, the gravity that you experience on the moon is far less on the Earth, and it would be the Earth would be far less than if you were able to walk on Jupiter. You know, as the thing gets larger, it starts to pull material in with a greater force, and they therefore accelerate more. Now, as the clump of material gets larger and larger, at some point there is enough pressure pushing down that actually the star sort of ignites. That's sort of the mainstream model. We have fusion at the core, and it has to require enough material to compress it down into a ball. The temperatures get high enough, and bang, you get fusion at the center of the star, and then it shines. That's sort of the accepted mainstream model. But there are problems with this model. And the first is, as if you imagine that you have this material that's sort of clumping down. If you can imagine, at the moment, the model very much sort of works along, I've got these magnets here, the concept of, as the material falls in, it sort of gets attracted and it sticks to it, you know, and it gets ever and ever larger. But, you know, if you imagine that actually, as this object gets larger and larger, the force with which some of these particles are being drawn in gets greater and greater. So imagine a lump that's sort of accelerating towards this one. As it smashes into it, it's not necessarily just going to stick. What is likely to happen is it will fracture it if there's enough force, and then you'll end up with two lumps. So you're no closer to solving this problem. And that's one of the biggest problems facing sort of the mainstream model is this idea as the object gets larger, that actually the force of the impacts will cause it to sort of split into more parts. So the only way they can get over that is they have to add in ad hoc sort of parameters that allow the incoming material to sort of slow down enough that actually it sort of gently caresses and joins with that original lump and doesn't sort of smash it into smaller bits. Also, the problem is that the mainstream model totally ignores, and it's slightly ironic that this is a magnetic ball, but it totally ignores the magnetic and electric forces. And I'll sort of explain in a little bit why those are important. But when we look at the object and objects falling into it, that is absolutely a force that we need to take account of. And the other problem is that if we look at this image to the side here, then this image shows a star forming region. So there are stars that are forming all along this sort of green and red line. And this is what we call a star filament. So we know that stars tend to want to form along these lines. And this comes back to what we've talked about before about this filamentation structure that we see across the whole universe. And the second thing is, in a lot of the more recent research that they've done into star formations, they realize that gravity in these sorts of areas doesn't play as significant a role as they originally thought. And in fact, the magnetic forces, the electromagnetic forces in these zones actually are highly important in terms of starting that initial collapse process. You know, it's not necessarily to do with random collisions, it's more to do with magnetic field lines causing charged particles to start moving in one direction and then initiating the collapse. But that's not built into that model. But we now know that that is something that should be taken into that model. Now, Hannes Alfvén is, I'm not sure that I've talked about him before, but he's one of the pioneers of looking at electromagnetic properties within cosmology. And, you know, he looked at this, 70 years ago, he started to look into some of these topics. And he had a separate theory based on the formation of stars, and then he also later looked at how planets were formed. Same process. So again, he assumes that there is this sort of interstellar gas cloud sort of floating about. But rather than assuming that all these particles inside of it are neutral particles, he assumed that they would be weakly ionized. And by weakly ionized, what I mean is that there are positive and negative charges within that. It isn't just a neutral particles. And that these charged particles play a very significant role in actually compressing this object down. They are sort of the initiating force for that. And he goes on to give an example. If we look at a proton, which is a positive charge, if we move a proton to where the Earth sits and we sort of allow it to orbit at the same speed as the Earth, then the force that proton experiences due to the magnetic force of the sun is 60,000 times larger than the force that it experiences due to the gravity caused by the sun. So significantly larger. Even if we move that charged particle, the proton, all the way out to Pluto, it's still 250 times larger than the force of gravity that it will experience. So therefore, we have to include these forces because they are important and they are significant when we look at these things. And interestingly, when they do some of the experiments on the International Space Station, looking at dusty plasma in zero gravity, indeed, they find these effects that they never thought possible. And again, it sort of shows that these forces are tremendously important to understanding how stars form, and later, as we'll look at, how planets form. Now, again, magnetic field lines, because of course, one of the assumptions that Hannah sort of talked about is the fact that the charged particles will flow along magnetic field lines. And you might initially say, well, there aren't any magnetic field lines. Well, this picture that you look at right here, which looks a bit like those images you see of the temperature in the sea. But in fact, this is the magnetic field lines of the galaxy. And the sort of the red line across the middle here, that is the plane of the galaxy. And the darker the color, so the more red it is, the stronger those magnetic fields. And you can see they are crisscrossed all across the galaxy. Now, any charged particle, if it's moving, will want to follow those magnetic field lines. So again, this will tend to override gravity in terms of its movement. So it is an important factor that does need to be taken into account. And again, plasma, when we talk about plasma, we are talking about plasma consists of both neutral material and charged material. And that charged material can be protons, but it could also be positively charged due to other effects, but also negative. So electrons, or again, negatively charged dust as well. And we'll look at that in a second. Important to realize is that, I mean, when we talk about charged particles, normally we talk about protons and electrons. And obviously a proton is a very small particle, and an electron is even smaller than that. But realize that these charged particles can affect or be affected by other things. And in fact, what you can end up with, if we take dust, for example, dust will readily absorb electrons. And by doing so, it'll take on a negative charge. So in fact, what you can end up with is a situation where you have large, heavy negative particles and, relatively speaking, smaller positive particles, which would be the protons. So the behavior of plasma isn't as simple as saying, we're just going to look at electrons and protons. You have to take into account the dust grain size and the charge of those, and what effect that has on the movement of the material in that gas cloud. So it's quite complex, but it is important that we do take that into account. So he sort of looked at this and he said, if you take this sort of gas cloud and you imagine that as the gas cloud slowly starts to fall inwards, and he very much saw that gravity still played a role in that collapse. But you imagine these particles start to move faster and faster. And as they're moving, they're falling in towards the central object. They'll start to collide with other particles. And there's a critical speed that he identified at which, if the particles are moving faster than this speed, what will happen is that it will cause other material, which is neutral, to become ionized. As it smashes into those, it knocks off an electron, and therefore that then becomes ionized. So you have sort of a cascade effect. As the material starts to fall inwards, more and more ionization starts to take place. And then what happens is these particles will start to want to follow the magnetic field lines. So again, it is important that we understand that and take that into account when we look at our model. And he looked at, again, at the grain size that we've talked about, and he looked at various different scenarios, and he determined how long it would take based on the grain size for a star to form, based on this idea that you still have a gravitational collapse, but it's sort of accelerated by these electromagnetic forces. And he came up with this idea that if you imagine taking a cloud which is, let's say, 5 billion kilometers wide, when you compress that down, it goes down to the size of only half a kilometer. So you have a massive compression of that material in order to form the star. And he said that when he did his calculations, if the grain size, so those dust particles that we talked about, if they are less than zero point 0.1 micrometers, it could take 1 billion years for that material to slowly sort of compress down and inwards. But he said if you end up with material that is about, you know, 1/10 of a centimeter in size, so very much visible, then it could happen as quickly as 10,000 years. And again, this is very different to mainstream, where it is this sort of very long and slow process for that collapse to take place. So again, taking account of the size of the dust particles is crucially important to understanding how quickly stars can be formed. And some may take a long time, and some might be much quicker than we currently think. Now, there is another idea. So that's sort of Alvan's hybrid model of the mainstream model. Then there's the whole concept of the electric universe, which is that effectively stars are birthed. If we imagine, we talked about these filamentation structures, and that we see stars forming along these filaments. Well, in the electric universe, these filaments are what we call Birkeland currents. So there is charge that flows, and it's not necessarily fast, but there is charge that flows along these Birkeland currents. And there are, let's just consider them flaws, some things somewhere in the galaxy, whether it's magnetic field lines that happen to cross, will cause a pinching effect on that Birkeland current. Imagine it's normally sort of a tube, and as it goes through a certain zone, it causes a sort of a compression in the center of this. And as it compresses it down, the material sort of gets funneled down, a similar sort of idea that you're compressing it down. But as it does so, it's sort of bridging two gaps. So where in the standard model and in Alvan's model, the star is still a fusion-powered star, in the electric universe model, it becomes an electric star. So this, you consider it more of a load on a circuit. There is, for simplicity's sake, like a short circuit occurs. A star is an imperfection in the flow of that current, and it's sort of emitting energy from that particular point, that imperfection in that flow of current. And that's important to understand, because when we look at the electric universe concept of how planets are born, that's very different to what we see in the mainstream. But again, the evidence for this is the fact that we do see stars forming along these filaments. You know, and we could spend quite a long time talking about electric stars, but I want to talk about planets. So for now, the concept is that stars are born through the sort of compression of these tubes of plasma, and at the center is formed an electric star, which to all intents and purposes looks like what we would call a star, but the idea is the inner workings of that star are very different from the mainstream model. So 3 different theories, one sort of very similar to the other, but sort of takes it in one direction, and then one very different to those. What evidence do we have for the formation of stars and for the formation of planetary systems around it? And again, it's important to understand that we've never seen a star forming. We never see that point of turning on. You know, and whether we're just unlucky or whether, it doesn't happen or we're never looking, I don't know. But what we do see is images of what are considered to be young stars with what they call protoplanetary disks, which they argue supports this concept. But I would like to suggest that maybe they are showing something else. But let's look at some of those images and sort of try and understand what the images are showing. So these are images, and these are, some of these stars are significantly far away, and some are closer than others. But what we see at the center here is that the center would be a dot, and you don't actually see it, but at the center would be the star. And what we see is the material around this. And again, it's important to understand that when this sort of spherical material starts to collapse, as it moves inwards, it starts to sort of spin. And as it spins, it will flatten it out as a disc. That's sort of the idea, which is why you see the disc shapes. In Alvan's model, you can actually explain that disc formation much easier using the magnetic field that sort of compresses and forces the particles to follow that thin disc. And again, the important thing to see is that there are these ring structures. There are black rings and lighter rings. Now, in the mainstream models, what they argue is that these darker patches are where planets would be forming. And obviously, as the planet sort of forms in that dust, it will attract material as it sort of orbits around it, and therefore it will clear sort of an area that it uses to build the planet. So you would expect to find in these dark areas, you would expect to find planets. Problem is, we don't always find planets in those darker areas. And again, here's another example, similar. Again, they all have these ring structures that seem to have these darker spacings in between them. This is a particularly interesting one where you actually see it's almost like a corkscrew coming inwards and it's sort of pinching in on itself. And again, the reason that the center is black is because they sort of black it out in order to be able to take that image because the star's too bright otherwise. So again, as we talked about, the darker zones, they believe, support the idea that that's where the planets form. And they remove the matter from the disk. But the problem is in a lot of these images, where we actually see the planets is not right in the center, which is where you would expect to see it. Where we actually see a lot of the planets is sort of on the edge of these bands. So not in the center, but still in where the material is. Now, Alvin took his model and he then modified it into what he called the jet stream model. And I mean, I've done a series of videos looking at his models, but effectively what he proposed was that as the material sort of compresses down and forms this disk, is actually what you would end up with is a series of these almost like elliptical disks, and they would sort of interfere with each other. But he argued that the forces on these charged particles would cause them sort of to compress, so they'd form what he describes as jet streams, like we see jet streams, you know, on Earth. You know, winds that are sort of restricted to small zones. And what you would effectively then expect to see is over time, as this material starts to gather, it would draw in. So imagine it's normally a flat disk, and as his system starts to work and the particles start to attract more particles, they'd actually draw and suck inwards. So his theory would be that you would absolutely expect to see these bands because these are what he would describe as the jet streams. And then in these jet streams, his idea was that this material would then start to clump and you would start to form various, which we do actually see if you look at that. There are indeed clumping formations along here. And it's those clumps which would form larger bodies, and those would then potentially collide with other bodies. And eventually you would only be left with one or two that would occupy a particular orbit. So quite a compelling theory, I would have to say, in terms of describing what we see in terms of the ring structure. But let's just take a step back and let's just talk about the ring formation itself, because at the moment we are making the assumption that these rings are left over from that initial star formation. Because again, remember, the idea is that this cloud collapses, forms the star, and then the material that's slightly further out forms this disk from which the planets are formed. But what if that's not the case? What if what we see here is actually something totally different? And I want to sort of point you towards the man that you see here is a man called Christian Birkeland. So he did a lot of experiments. He was fascinated by the auroras, and he built lots of experiments to try and mimic the auroras. And he believes in the end that actually what we see as the auroras was caused by plasma and electricity. And one of the experiments that he conducted, he produced these ring-like structures around his sphere. So again, this is filled with plasma and dust, and you end up with these rings. And kind of when I look at it, I go, that very much looks like, and I've got the image next to it, like Saturn. But what if, I mean, this is obviously what he's doing in order to do this. He's causing an electrical input into this device, which is creating these rings. So let's go back to this image of these disks. So what if these disks are not planet formation at all, but instead are like a fingerprint of the fact that some electrical activity is occurring or has occurred in there, and that could be that the star has only recently formed. As we said, the sort of the pinching structure, and that there is a sort of residual electric field which causes the material around it to start sort of grouping into effectively what would be the field lines around that particular object. I mean, to me, that's quite striking. That does beg the question, and it's something that we'll come back to, is why does Saturn have these very pronounced rings and yet the other gas giants don't. I mean, they do have rings, but they're nowhere near as pronounced as those on Saturn. So again, is that some indication of something that occurred to Saturn in the more recent past compared to the other planets? Again, something that we will come back to. So what does all of this have to do with planet formation? Again, the important point to note is that the mainstream model says that these disks that we see form around new stars, and that from these disks, the debris forms planets. So slowly over time, the same sort of process, but on a smaller scale, in the dust in these rings then sort of collapses down and forms chunks, and the chunks attract larger chunks, and so a planet is formed. But it doesn't necessarily prove the hypothesis, because there are problems with this. Now, again, as we discussed with the magnetic ball, as you start to attract, or as you deal with smaller and smaller bodies, the forces of attraction become smaller and smaller if all we're requiring is gravity. And the problem is that when you're dealing with smaller bodies, is how do you end up with something that's as beautifully spherical as a planet? You know, why don't we end up with bodies which are, you know, like this, quite lumpy? And why is it, again, the same idea, why do they not get smashed apart? And again, in order to overcome this, they have to introduce these ad hoc assumptions to slow down the material, to allow that you know, growth process to occur without smashing the planet apart. Now, Alvan was the only one, if we, you know, look at the models, who was able to overcome this problem, because in his idea of these jet streams, what actually happened with the material is you almost have like an electromagnetic braking force on these materials. So as they sort of form these streams, the material actually starts to slow down, and as it slows down, that allows the material then to be attracted to each other, either through electromagnetic forces or due to gravity. But what about the EU model? So if planets are born in the mainstream model through, again, the same process of sort of compression, Alvan is the same idea, but with a slight modification. How are planets born in the electric universe model? So again, it's important to understand that when we look at stars, and particularly our sun, the idea is that they're powered by electric current. So they're sort of an electric discharge phenomena. Now, a sudden sort of change in that incoming current can cause a sort of a stressing on that sun. And what will happen, if you imagine you're dumping a whole load of extra charge into this body, and let's say there's not enough area for it to sort of radiate out that electric discharge. So it has to try and get rid of it as quickly as possible. And that's what we see here in the image is what we call a CME. So it's a large ejection of material from the star. So this is a very small stressing event. But if that stressing event becomes large enough, then in fact, if you make it so large, what can actually happen is the star, what it wants to try and do is have a surface area that is able to radiate, that allows the current to flow outwards easily enough. And when you have a large sphere, the surface area is actually smaller, and the efficient way to do it is to actually split it into two. When you split it into two, you have a greater surface area. So what stars can actually do when you have a huge increase in the incoming current is they split in two. Now you might think that sounds a bit sort of crazy, right? If we look, and again, I could spend a whole series of you know, talks talking about this, but there is evidence when we look at stars. A lot of stars that we see are binaries. Why are they binaries? Again, in the standard model, you know, that just happens to be that two clumps of gas formed close enough and then they sort of gravitationally caught each other. In the electric universe model, that's because, you know, a lot of these stars have undergone these stressing events and they split. And sometimes they don't split evenly, so you can get smaller and larger companions depending on how that sort of incoming current is shared. And if we look at historic records, and if we look at stars, I can show you many examples of stars that have changed color rapidly over a period of time. And then when they observe them, all of a sudden, they're able to spot the fact that it has a companion, which it didn't used to have before. So this does suggest that this possibly is a mechanism for allowing the star to cope with a sudden change in that incoming current. Now, what does that got to do with planets? Well, the same thing can happen with planets. So again, if the electrical stressing event isn't as large as to cause it to split, what can happen is that it can actually, again, consider the fact that if we take a star and make sort of the split much smaller, what is the difference between Jupiter and the Sun? I mean, the constituent parts are effectively the same. So what can happen is when it's so uneven, is that actually the star can eject what we would then call a gas giant. And again, the evidence for this, when we look at certain stars, particularly younger stars, or what they call younger stars, we often see gas giants orbiting very close to the parent star. And they tend to be very hot initially, which would make sense if they've just been ejected from an electrical stressing event. And they later then migrate further outwards, which again, when we look at our solar system, there's many questions to answer when we look at that. So that's a gas giant. So how do we get planets? Well, again, the same thing. Again, you have to sort of consider that in the electric universe model, that the gas giants are still connected to this sort of incoming current system. So, but to a much lesser extent, not enough to make it shine, but enough to still has a trickling in of current. And again, if a sudden incoming current sort of pulses and causes that increase, and let's say that only goes to the gas giant for whatever reason, or that the star can easily handle it, it could cause the sort of the center of that object to emit what we would consider to be a rocky body. Because again, at the center of if we look at Jupiter, we think the center of Jupiter is very much like the Earth, a sort of a rocky body. So could part of that split off and be ejected outwards? That's the electric universe model. Now, there are caveats with this model. And the problem is that, if I'm being very honest, it's not particularly well documented. There are lots of people that talk about it. It makes a lot of sense in a lot of cases. But again, understanding the mechanisms around when this happens and why this happens is not particularly well documented. Mainstream requires lots of ad hoc assumptions. And Alvin's model is closely aligned with mainstream and holds many clues, but it can't really answer when we look at our solar system. And again, looking at our solar system throws many more questions up. If I'm honest, I think the answer lies somewhere in between these models. I don't think anyone's necessarily got it all right, but I don't think the answer is any one of those in particular at the moment. A lot more work needs to go into understanding what we see out there. So what can we learn from our own solar system? Now, the strange thing is when we look at our solar system, it's very unique. When we look at other exoplanet systems, they don't look anything like our system does, which is kind of strange. We have rocky planets at the interior. So these are all considered rocky planets. So Mercury, Venus, Earth, and Mars. We then have this asteroid belt. And then we have the gas giants. And again, as I said before, that's sort of the opposite way to where they believe that they form. It's believed that the gas giants form closer to the star and then slowly migrate outwards. So what do? A swap? Do they suddenly decide, I don't want to be here? I tell you what, you go here, I'll go over there. And then you have further out, again, more rocky bodies. And then you have this, what they call the Kuiper belt, which again is another huge asteroid belt. And then even further out is what they consider the Oort cloud. Now, I'm not convinced that there is such a thing as an Oort cloud because it's not based on any measurements. We can't actually see them, but it's believed that this is where some of the comets lie and they fall inwards, and that's why they have such eccentric orbits. And the idea and the reason that it's spherical comes back to that original diagram where we looked at that sort of the image of the gas cloud sort of collapsing inwards. The idea with this is material that was far enough away that it didn't actually fall inwards. So it just sort of sits there, but yet they're still lumps. So how do they form as lumps? So again, it's a slightly convoluted story. But again, that is part of the system we believe. And even if you don't believe in the Oort cloud, we still have comets that you have to take into account, which have very eccentric orbits. They don't, again, most of the planets, when we look at them, they all sit on the plane. They all sit in a very similar place, except for the comets that take a very much acute angle in. Some of them are directly down and out and underneath. So again, you have to try and explain those. Yeah.
I just want to add to that because some of these other planets like Iris and others that have been discovered, or planetary type bodies, they have bizarre orbits also, some of them. Very
Yeah.
odd and not anywhere near what we're looking at with Earth and the other major planets. I wonder why that is.
Well, I mean, this comes back to the question of how they form, and to be honest, no one really has a particularly good answer that explains the, let's call it exoticness of our solar system. Now, to be fair, and we'll look at an example in a minute, our ability to see other systems is very much limited. So we don't have the ability to really see the way that we can see our planets. We see them as sort of dots, and we make assumptions based on the light we receive as to sort of, what composition they're made of and how large they are. But even within our solar system, as you point out, there are very weird asteroids that have very peculiar orbits that behave, some of them behave a bit like a comet and a bit like an asteroid. So there's lots of things that we have to try and account for in any model. And I don't think any model at this stage can account for all of those. And again, if we look at another weird thing, if we just look at the planets, then the weird thing is that there are sort of two categories, predominantly of angles, and these are the angles that they orbit at. So if we look at Mercury, Venus, and Jupiter, they're all pretty much upright when we look at the way they orbit around their axis. Obviously, Earth, we're sort of inclined at 23 degrees. Mars is 25, Saturn 27, and Neptune at 28. So, is there any clue in that? I don't know. Why are those similar to others? Obviously, in the electric universe theory, the idea is that some of these were part of Saturn, which was a separate star system which joined us, and that's why our inclination is the same as Saturn. That's possible. Again, we don't necessarily have definitive proof of that, but it is odd that some of these have a very different inclination. Like if you're forming them through collapse, then why do some of them tilt? I mean, obviously, the mainstream model tries to explain that by meteor impacts sort of tilting it to one side, or large objects colliding with them. But why is it basically two different groups? I mean, Venus you can sort of ignore because that's actually upside down. So again, Venus is a bit weird because, I mean, how do you determine that it's upside down? That's more to do with its sort of magnetic field. So there are oddities in the solar system. Again, if we look at magnetic fields, they're weird as well. If we look at the alignment of the magnetic field, they're not necessarily the same as the angle of the planet tilt, which is particularly strange. If you look at Jupiter, it's sort of almost like it's being pulled over to one side. And they sort of argue that the gas giants have, well, we know that they have magnetic fields. That the reason for the magnetic fields is different in each one, which is particularly strange because why is the formation of the one on the Earth so different to the one in Saturn or the one in Jupiter? Why do we not have the same mechanism? And again, the mainstream model can't account for that. If we look at the electric universe concept, then these are all electrically powered. So as long as you get power, you would form the same sort of magnetic field. Doesn't necessarily explain everything, because then why does Mars not have one? So there are oddities in all of these theories. And for me, it's somewhere in between these that we need to look for the answers. I don't think anyone holds the answer to all of these questions. Again, if we look at composition, so the sun is 75% hydrogen and 15% helium. Jupiter is close to 90% hydrogen and only 10% helium. And then Saturn is 93% hydrogen and only 3% helium. And then Neptune is 80 and then 19. So again, we see sort of a consistency between the Sun, Jupiter, and Neptune to some extent. There are some differences. But the big difference we see here is in the helium composition from Saturn, and to some extent Neptune, I suppose you could argue. So again, do they tell us anything? Again, if this forms from one cloud, why do we have such differences across these planets? Even in if we're talking about the EU model, if they are ejected from stars, why are they different? Well, you could argue in the case of Saturn that their theory is that this would be a different star, and therefore the composition of this should be different, which again you could say that does sort of point in that direction. But again, in the case of Jupiter and the Sun, why are they not identical? Why is there differences? Now, there may be other processes that go on that explains that, but again, no one has written everything down in one place that you can go and find all of this information. It's a clue. Sure enough, it's a clue, and we need to try and sort of unravel that mystery.
All right, I hope you're enjoying the presentation. Make sure to join us for parts 2, 3, and 4. We will be discussing the electric universe, showing how planets could actually be hollow and the Earth could very well be hollow. This is fascinating. We're going to talk about the effects of Saturn, the mysterious rings. We're going to talk about the possibility of artificial creation or intelligent design outside of the universal order. Giant exoplanets disappearing. Where did they go? A lot to talk about. So I'll leave the link specifically in the video description box. You're amazing. Hit that bell. Be well. Also, check us out for exclusive content on Patreon and LeakProject.com. Over 3,000 podcasts, hundreds exclusive to LeakProject.com. Be the change you want to see, everybody. And remember how awesome you are.